Welcome, everyone. Before we begin, I just wanted to say that AM2D and Monash University, Clayton, wish to acknowledge the people of the Kulin Nation on whose land we are gathered today. We pay our respects to their elders, past and present, and I ask that those of you online pay respects to the traditional owners on the lands which you are situated. Welcome to the second Talk 2D seminar right here at the end of the year. You should be able to see a screen on the screen, a QR code. Please scan it. It'll take you to our LinkedIn page so you can follow us. I'd like to ask Professor Mainet Majumdar, the director of AM2D, to introduce our speaker, and there'll be time for questions at the end.
Thank you, Phil, and my warm thanks to Sebastian for taking the time to give this talk. So Sebastian is the Vice President of Automotive and Business Development at Skeleton Technologies. He received a diploma in chemistry in 2012 and a PhD in physical chemistry from the University of Münster in 2014. So from 2016, he had been working with Skeleton Technologies and developing cells, supercapacitor cells. And he has been a major influence in the company, winning research and innovation grants worth over 50 million euros. He has authored several papers, but most importantly, there was a paper he wrote in this year, actually. And that was part of the reasons why I thought he might be a really good candidate to give us a talk. And essentially, he is talking about metrics and methods for moving from research to innovation in energy storage. As you are all aware, supercapacitor is a very busy area with a lot of research and development going around the world. But there is more to it than just being material scientists and materials research. In this paper, he talks about very important aspects. For example, materials innovation or cell innovation is more than the development of the active materials. Active materials play a part, but there are many different steps which can also needs innovation, actually. And some of these innovations could be low-lying fruits which can help get better and more efficient products. And in that article, he also produces recommendations to academic researchers on how to do the reporting and how to do proper analysis that it would make more sense and more impact. With that, I will ask Sebastian to start his talk. Thanks.
Yeah, thank you very much, Malek, for the kind introduction. I will also share my screen. I hope this works. Give me a second here. Can you see my screen now?
Yes. Great.
Yeah, so again, thank you for the kind introduction. The article that you mentioned is something that has been, let's say, close to my heart for a longer time, because transitioning from academia to industry, I have learned quite a bit about what kind of data and especially data presentation matters when you're trying to transform an invention to an innovation, which means bringing it to somewhere where it creates actual value. That is a little bit also what I will talk about today. I will focus on nanocarbons in this talk and talk a little bit how nanocarbons can be brought from invention to innovation. I will also give you a little bit of introduction about the company that I work for, Skeleton Technologies, in case you know the company. Yeah, I will jump right in. So Skeleton Technologies is a scale-up, what you would call it today, not a startup anymore. Founded in 2009 in Estonia, so north of Europe. And Skeleton was founded with one big idea in mind. And the idea was to solve the challenge of electrification and zero-emission technologies. And of course, that's big picture talk and a big idea behind this. But the solution on how to solve this challenge is, of course, lies in so many different fields. But one concrete field, one concrete thing that you can do is you can work on energy storage. Yeah. And energy storage, of course, is today, most of the time, lithium-ion batteries. Lithium-ion batteries are everywhere, from electric cars, from your cell phones to laptops, also in stationary energy storage devices. The main point that we see today, and that we also saw when the company was founded in 2009, was that lithium-ion batteries alone cannot do it. So lithium-ion batteries alone, they are great technology for the applications that they are mostly used in, for example, electric cars. But there are other applications and other requirements that lithium-ion batteries cannot fulfill really nicely. And with that idea in mind, Skeleton was founded with only a material at hand. So there were the 3 research scientists who kind of got the material in a lab, and they knew, okay, these are the material properties. It's a very nice material for supercapacitors, probably can be used in other things as well. And the 2 entrepreneurial co-founders that then joined said, okay, we will bring this material into the supercapacitor and increase energy density. And that material is called curved graphene. Of course, every physicist will now say graphene is never curved, it's always flat, which is also true. But you can imagine this material, I'll later talk a little bit about it, as kind of a graphene sheet that has been crumbled up like a piece of paper, and retaining most of the graphene properties like sp2 hybridized carbon atoms, and also good conductivity and fairly high surface area compared to, for example, activated carbons. So where's the company today? Founded in 2009 in a quite small room with 5 people. So today we have the largest and most modern supercapacitor factory in Europe, and we're currently building the largest supercapacitor factory globally, also in Europe, in Leipzig, in Germany. We have today a little bit over 300 people. We have our supercapacitor products firmly in the market. We have the products are in the field already for several years, and they're working well. Customer feedback is good. Of course, then we're currently scaling. That's why I would call ourselves not a startup anymore, but a scale-up. We also have some other facilities, for example, in Bitterfeld-Wolfen in Germany, in the chemicals park. We have our curved graphene synthesis and production plant, which is also currently being scaled further. And here in Tallinn, in Estonia, where I'm sitting, we have a lot of the back office, but one crucial part of energy storage, especially of bringing innovation really to the end user, is software development, electronics engineering, and modular and systems development. So it is also something that myself as a chemist has a long time ignored and thought, okay, the real innovation comes from the cell chemistry. But it is astonishing how much innovation and how much invention also is necessary on the software, on the electronics engineering and module and systems development in order to build the best product for the end customer and to create the best solution really in the end that is most energy efficient and most cost efficient as well. So let's take a step back and talk briefly about what supercapacitors are and how they're different from lithium-ion batteries. If you just start from the materials that go in without knowing anything about how they work, then you will realize quite quickly the general concept is roughly the same. You have 2 electrodes, they are separated by some kind of separator, and you have an electrolyte in between. The whole thing is encased in some kind of casing. However, if you then analyze the materials, then supercapacitors use fairly simple mixes of materials. So whereas in lithium-ion batteries here on the left side, you have mixtures of carbonates and additive as electrolytes, you have even composite separators, but more importantly, you have very complex electrode formulations with graphite on the anode, metal oxides on the cathode. You have different current collectors like aluminum on one side, copper on the other side. And you have a lot of different materials in there like nickel, copper, cobalt, or manganese. Then supercapacitors are fairly simple. You have aluminum foil on both sides coated with a porous carbon. Most of the time, this is activated carbon made from coconut shells. And you have a paper separator that separates the 2 electrode, and the electrolyte is most of the time, in 95% of the cases, acetylnitride based. And that's about it for the industrial supercapacitors that you can buy today on the market. So this main difference in materials, of course, sparks the question, okay, where does what's the difference in terms of energy storage? So how do supercapacitors store the energy? In lithium-ion batteries, of course, you have an anode and a cathode. The anode today, most of the time, is graphite. It's today also starting to be doped with silicon. So there's a lot of innovation happening on the lithium-ion battery side as well. And you have then on the cathode mostly some metal oxides that store lithium, and upon charging the battery, the lithium is shuffled into the graphite. And upon discharging, it leaves the graphite. It goes into its preferred state into the metal oxide. So since you move a charge, of course, you have to move a counter charge, which is then the electron flows, which is the electricity that you can use. In supercapacitors, it's a little bit different. Supercapacitors use an electric field to store energy, which means that you actually only need an electrode surface and a mix of ions on the other side. And the ions are in the electrolyte. So what happens when you charge up that surface is that the ions move to this surface, the counter ions move to the surface and form what is called the electric double layer. And the electric double layer, or electrochemical double layer, is, if you look closely to it, then it is a capacitor in itself again. So you have a positive charge and you have a negative charge here, and they are separated, they're not joining. So this thing here alone is already a capacitor. If you then look at this from a more schematic perspective, then what you have in a supercapacitor is actually two capacitors. You have one on the positive electrode, one on the negative electrode, and the opposite side of these capacitors is formed by the electrochemical double layer. That's why supercapacitors are often called EDLCs, or electrochemical double layer capacitors. And how this looks like, if you look at a respective equivalent circuit, then this equivalent circuit would look like this: that you have a capacitor and another capacitor, and they're separated by this resistor here, which is the electrolyte itself. That's about it, how a supercapacitor works. It's quite simple. Charges are stored on the material surface. You have no electrochemical interaction, actually. Ideally, you have no chemical reaction or electrochemical reaction happening, and it's a very stable system. In lithium-ion batteries, however, you move lithium ions into materials, you move them out of these materials every time you cycle. And I will later get into the relation of these two mechanisms also to the properties of the actual device in the end. So if you look into the properties of the devices, then lithium-ion batteries, of course, because you store these charges in the bulk material, have quite high energy density compared to supercapacitors, around 20 to 30 times higher, depending on how you look at it, which materials you choose, even up to 35, 40 times higher if you choose the really, really new lithium-ion batteries that are now coming onto the market. But they have very limited power density, and that also makes sense because you need to move these lithium ions out of these electrodes and out of these material agglomerates into the electrolyte and then over to the other side. Where in supercapacitors, you have a very easy time moving a charge away from a charged surface to the other side, to the electrolyte, to another charged surface, or just back into the electrolyte, which means normally very high power density. So very high mobility of the charge carriers means very high power density. That makes supercapacitors and lithium-ion batteries kind of two technologies that are very different to each other, in the sense that one has very high power density, one has very high energy density. But there are other things to look at. Also, cycle life, for example, since you have in lithium-ion batteries two materials that constantly are basically used as a shelf for energy storage. Yeah, so you always put something in, you take it out again. This is a wear and tear on materials, which means that you have limited cycle life. Today's lithium-ion batteries, depending which chemistry you use, you have around 3,000 cycles. Some of them have 5,000, 10,000, even 20,000 cycles. But compared to supercapacitors, there's barely nothing, because you have way over 1 million cycles with supercapacitors, and in industrial devices, easily 2, 3, 4 million cycles. That also carries over to the safety. So supercapacitors, since you do not have any electrochemical energy storage, you have very high safety. You don't have any lithium inside them. So you don't have the general safety risks normally attributed to the metal oxides that you have in lithium-ion batteries, or to the lithiated graphite that you have in lithium-ion batteries. That also means that both of the technologies are aiming at very different applications. So you might ask, okay, if you cannot store a lot of energy, where do you actually use supercapacitors? And the applications that Skeleton Technologies today uses supercapacitors in are quite well distributed through a lot of industries. So we have, for example, the automotive industry, we have transportation and heavy equipment, grid and renewables, and industrial as the 4 main segments. In transportation and heavy equipment and grid and renewables, I can say that today they are the largest markets, but this closely followed by industrial, and automotive today is rather a niche application, but is also going quite nicely. So where do you need a lot of power but not a lot of energy? One main field is kinetic energy recuperation, or short KERS, so kinetic energy recuperation systems. These are used throughout all of these fields. So you have kinetic energy recuperation systems for light rail, where we are supplying to Skoda Electric and to Metcom. This is mostly on trams in cities. You have kinetic energy recuperation for port cranes, for forklifts, for elevators. You have kinetic energy recuperation in automotive applications as well. And you have even kind of kinetic energy recuperation in grid and renewables, depending on which exact application they look at. Another application is, of course, just anywhere where you have a high power peak. So that is engine starting. A lot of supercapacitors today go into cold countries like Canada, north of the US, but also Northern Europe, in order to start diesel engines. They replace normally lead-acid batteries. So they replace a lot of lead-acid batteries that otherwise need to be exchanged constantly because of poor lifetime. In grid and renewables, you have basically you have the application where you help to stabilize the grid, so that more renewables can be integrated. So if you integrate more solar, more wind, you normally destabilize the grid, because these are not so-called reactive sources. They cannot really bring in a lot of power when you need a power peak. That is then where the supercapacitors can be used. In automotive, you have things like the 12-volt board net, but also 48-volt active suspension. So these are especially 48-volt active suspension is rather a niche application today, where it is about really high power electrical actuators stabilizing the car. So you can see there's a lot of different applications where the technology itself has an impact on saving carbon emissions or enabling other applications to save carbon emissions. And the important here is that there is a certain application fit. So you look at what does the technology offer? It offers very high power, it offers very long lifetime, but it doesn't offer a lot of energy density. So you pick the applications where you do not actually need energy, but where you need power. And I think the most important thing is here that we often get the question, will supercapacitors ever end up in electric vehicles in terms of traction batteries or driving actually the vehicle? And then we clearly can say, no, this will not happen, because lithium-ion batteries are very good for that. They're very, very energy dense, and especially in an electric vehicle where the 3,000 to 5,000 cycles, charge-discharge cycles, are definitely enough over the lifetime of a vehicle, then it's not really needed to use supercapacitors there. Supercapacitors don't really offer an advantage, and we would rather use them in the other applications where lithium-ion batteries fail to bring a significant advantage. Skeleton today does everything from raw material to systems, and that's also a little bit connected to this talk, where I will talk a little bit more about the raw material itself, activated carbon or nanoporous carbons, and also our curved graphene material. We transfer this material into electrode, into single cells, into industrial modules, into systems, which has taught me a lot about how to think holistically when you start from the material level, and to understand when you change something on the material level, how do you translate that to an advantage on the system level, because the system is normally in the end what the customer gets. For some customers also get the module, but somewhere here the advantage needs to be created on that right side for the end customer. If you create an advantage only here, this advantage is for you only. The end customer might not see it. Yeah? And that's what I'm going to talk a little bit about later as well. So if you look at the current energy storage devices or technologies that are on the market, then you have the supercapacitors, you have high power batteries, and you have high energy batteries. And of course, you can divide those into much smaller groups as well, and many more groups here. But this is the general energy storage, electrochemical energy storage market. You have the fuel cells as well. I didn't put them here because the fuel cell is not a storage device, it's a power conversion device. So you can basically convert chemical energy stored in hydrogen and oxygen basically into electricity, but it's not energy storage. The storage doesn't happen in the fuel cell. So the high energy batteries are what you normally find in electric vehicles today, what you often find in your smartphone and in your laptop. They have quite a low energy density cost. This is a great advantage for them. So if you just want a kilowatt hour, then they are normally the cheapest. But they have low cycle life, and they have normally long charging times. So from your laptop or from your phone, you normally know this, that you take an hour or longer to charge, an hour already being fairly fast. High power batteries, on the other hand, this is the LTO batteries that you can see mostly. They have they're in the middle, so you have like medium energy density, medium efficiency as well at fast rates. But you can charge them relatively fast. So we're talking here about 5 to 10 minute charging. However, they still don't have the longest lifetime. They have longer lifetime than the high energy batteries, and they have normally quite high initial costs. So at cell level, at least 600 euros or dollars per kilowatt hour. They're quite good in safety. So that's the one thing that the high energy batteries normally don't do well, is safety. Supercapacitors, on the other hand, they are extremely safe. They have extreme high power, and also one thing that I didn't mention before, they don't use really any rare earth materials. They don't use lithium. They don't use cobalt. So they're very sustainable in terms of material use, which the high energy batteries are really not. They lack two things though, and one thing that I haven't talked about is the scale. Scale here is basically just an arbitrary indicator on how much scaled is that industry. If you want to buy 1 million battery cells today, it's no problem. You will find plentiful suppliers that will fight about how to supply you. If you want to buy 1 million supercapacitor cells today, then we will happily supply you. That's not a problem. But the problem there rather is that the scale is not at the size of the battery. So you don't have the same gigafactories, you don't have the same infrastructure and the same kind of supply chain infrastructure that is currently being built up by us as well. So that's what these two arrows stand for. So we work on the scale actually. We want to get to the scale of the lithium-ion battery industry to have something equivalent to a gigafactory. The other thing is energy. So supercapacitors don't have a lot of energy, very low energy density in terms of kilowatt hours per kilogram. But that is also something that we are working on. So with our curved graphene material, that's exactly where we want to go. So how do we work on these two items? I want to focus today a little bit more on the energy side, because the scale side is clearly just taking the lessons of the high energy batteries or lithium-ion batteries and applying them to the supercapacitor world. That's more of a process topic, not a material topic. But for energy, it's quite obvious that it is a material topic. So for energy, if you want to increase the energy of an energy storage device, then there are a bunch of things that you can do without changing the materials. You can change the cell design, you can change the electrode design, and so on. But if you want to have a fundamental change, you need to work on the material. And that is also what is at the core of Skeleton, because Skeleton was founded on a material research, is that we do material research, and we use material research in order to bring higher energy storage or higher energy density to the market. So that's also why I want to talk today a little bit about how to bring something that is an invention, so something new in the laboratory, some new idea that works even in the laboratory, and you have something very nicely, to an innovation, which means to have something actually create value for our society, to create value for our customer, to create value for somebody on this planet. And that value is not always money. That value can be CO2 emissions saved, that value can be sustainability, it can be something else than money, but it is something that improves something existing. So I want to talk today a little bit more about graphene supercapacitors and the curved graphene material, and about how to move from this invention to an innovation. We also have worked on super batteries. I think you can find online some talks about this as well, where we actually move into the direction of building a high power battery based on the experiences that we have from the supercapacitor market. This is something that really deals with the energy density issue. So you actually get around 10 times the energy density that you have in supercapacitors. But my focus will not be on the super battery today. So if you want to learn more about that one, I suggest to go to our website and have a little bit of a look on the materials there. So today, let's talk about graphene supercapacitors. If we use curved graphene in our supercapacitors, we get around 72% increase in energy density compared to what today is on the market. And we still keep all the advantages, like all the life cycles and the ultra fast charging times and everything. So the question is, how do we get there? Yeah? How do we get to this increased energy density? So what we do is we use a different material. But what does this mean? So why can we just use a different material and then get to a higher capacitance? The reason is, of course, we use a material that has higher surface area and at the same time can still be used in the same way that we currently use our activated carbon. So since supercapacitors use an electric field to store energy, then they are dominated by this equation here, where you have the capacitance of supercapacitor, which is in turn dominated by the surface area and the distance between the charges. And the distance between the charges is crucial here because it's the distance between the charge on the electrode here, positive charge in this case, and the charge of the ion. So it's not the distance between the actual two physical electrodes in the supercapacitor, but it's the distance on how close can this ion come to the surface area. Since the, sorry for jumping here a little bit, since the equation here has these, these items here, we can block them out, they're constants. So it's only dependent on surface area and distance between the charges. And the charges are stored on the material surface. In case of activated carbon, that means that they are stored in the porous structure of carbons, and not only activated carbon, but any microporous carbon. So normally what you have in a supercapacitor, you have some kind of carbon material which is microporous so that you have a large surface area. And we really talk here about the so-called micropores. They are called micropores, although they're in the nanometer range, which is always a bit confusing, but the nomenclature is that they're called micropores. They are under 2 nanometers, and that's really where most of the energy storage happens. All the other pores are rather transportation ways to the micropores. So they impact definitely the performance, but they do not impact that much the capacitance of the carbon. And what you want to do is, of course, to increase the surface area available to these ions. So you would say that if you increase the surface area, you most probably will get an increased capacitance, and you're right about that. So we did this together with Andrea Balducci from University of Jena, who's working on supercapacitors for quite some time. We did this test here where you use different carbon materials, and You use them with different surface areas. So here we use the BET surface area method. And you increase the, so basically you take different carbons and measure the capacitance. And you get kind of this correlation of, okay, you have higher surface area, higher capacitance, but you get some outliers as well. So it's a correlation, but it's not a very straight correlation. And what we did then is we checked what is actually the influence of this pore size. So how can you actually impact that capacitance by changing the pore size? And we found that actually for different pore sizes, you get also kind of a sorting after capacitance. And what happens here is that if you have pores that are way too small, then you actually get not enough capacitance because the ion just doesn't fit in all the pores anymore. So the average pore size is too small for the ion, whereas when you get to because these were all done with the same electrolyte, when you get to a higher pore size, larger pore size, then you can actually get the ions in and you can utilize the surface area. So the impact of this pore size in the end played a huge role because you actually might have carbon materials that have very high surface areas, but low pore sizes. And this is exactly what happens here. Basically, these data points here, where you are just on the brink of having the pore size large enough, but you actually have quite high surface areas, but the surface just cannot be utilized. So again, here it is to actually check, it is about to actually check what is the capacitance that you get out, not only what is the surface area, but what is the actual value that matters in the application, which is capacitance. One thing that I always want to mention here when I mention BET surface area is that you still see today a lot of publications where you have BET surface areas larger than 2,600 square meters per gram. If you ever measure this, then I would always ask you to not publish it because it is a nonsensical value in the sense that 2,630 square meters per gram is the maximum of any carbon material that you can have. If you have a carbon material, then the maximum surface area that you can get is that of flat graphene. And that is 2,630 square meters per gram. If you get a higher value, then it is because the BET surface area is very treacherous when you go into microporous materials. So BET surface, the BET calculation does not really treat the micropores well, especially if you have very small pore sizes and pore sizes around 1 nanometers, like higher and lower. There are a lot of effects. I trust you to read up on this topic if you are interested, because that is another 10 talks on their own where you can talk about BET surface area. So how does curved graphene look like? What we realize is that energy storage in ultracapacitors or supercapacitors takes place in very small micropores, around below 1 nanometer. Is very good for the common industry electrolytes. The electrolyte that we were using in the other study was a slightly different electrolyte. And if you have standard materials like activated carbons made from coconut shells, then normally those provide a mixture of pore sizes. So you have like here in gray, the standard activated carbon with different pore sizes that you find. They'd always try to get a pore size of around 1 nanometer as well in these activated carbons. But what we managed to do with curved graphene is to get like one peak basically here. That is, yeah, it's a little bit split, but it's basically one big peak of pore sizes that are very well defined. That normally brings you the increased capacitance, and we have the proof that in an industrial large cell, instead of 3,200 farads, we get 5,000 farads when we use the same amount of curved graphene compared to the amount of activated carbon. So that much about what we actually do in terms of material research and what to consider when you actually work on these material research. That was a very short excursion. Again, these things can be elaborated on much further in-depth talks, but just to give you an idea what things to even look out for in a very simple way, you can, if you look at only one property, most of the time you're making a mistake unless that is the property that the absolute end customer is utilizing. If it's energy density on an industrial device, for example, then I would agree that you can look at that property always and say you have made an impact. If you talk about the impact beyond the material characteristics, then what I want to say here is that you normally have an impact beyond that. So there's much more than surface area and pore size to a material. Then one has to consider a little bit how academic research normally works. And of course, this is simplified, but normally you have a theory, you try to prove or disprove your theory in experiment, you do analysis on it, you get a result, and in the end result normally is a publication. And that's what in academia you normally aim for, is a publication. Maybe it's a research grant as well, but this is a publication in itself as well. This differs a little bit from industrial development, which I want to make the differentiation here between the research and the development part, because industrial development normally takes the result out of academic research and aligns it with a product strategy, a company strategy. It checks into market requirements, into the available market. So you might have a technology that has amazing values versus everything else that you read in publications, but you look into the markets and you see, okay, there's a market of maybe 20 people in the world that will use this, then you will probably not build a company out of that technology. And in the end, you take these two things and make product development out of it. So you take this academic research result, or also industrial research result, and you develop a product based on this. That's important to remember, because the goal of industrial research and development is not the publication. The goal is the product. So the one main difference that I saw when joining company and working then in industrial development, where in contrast to the academic research, was really that there is a lot more scrutiny on the validation of the results, and there's much less focus on how you present your results, but much more focus on what is the real-world impact of these results in the end. Because in the end, somebody will put money into this, or you have a nice result. Somebody will have to take money, put it into the development, and if the end result, the product, does not work, then that money is lost. So if we apply this to electrodes in supercapacitors, then the one thing that I can bring as an example is electrode structure, or electrodes in general. So if you just take this graph here and have a look at these different carbons that are all, I think most of them actually not on the market anymore, but this was from 2016, so 2015 even, so very early in the company, when we evaluated different carbons. And you would, of course, now just say, oh, let's take this one here. It has the highest volumetric capacitance. And by volumetric, this is already the first step, because in an industrial cell, you have a fixed volume. So high gravimetric capacitance, but a low volumetric capacitance might not bring you anything if you don't have the space where to put this material. So that's the first thing. We normally look at volumetric capacitances in supercapacitors, because you take one thing out of the equation, which is how do you make your electrodes? So you stop looking at the material side, you already look at the electrode only, because volumetric capacitance is capacitance in your electrode layer, your coated layer. So you would now say, let's take this material here because all the others are worse. So the one thing that matters here is that the electrode structure is important. So an electrode which has very low volumetric density versus an electrode that is really high density is normally worse off. So you can have very high gravimetric energy, specific energy or specific capacitance. If you cannot get this material into a confined volume well enough, then other materials with lower gravimetric capacitance will fare better in the actual application. And back to these carbons here, then what I can tell you is that in the end, we chose one carbon here in the middle because you gain maybe here a couple of, well, not even a couple of, but like 20–30% of energy. But you always have to put this against the cost. And I can tell you that the cost here is not just 30 or 40% higher, but even a factor of 2, 3, 4, 5 times higher. The one thing that was very important for us in terms of bringing an innovation to bringing an invention to innovation is that electrodes need to be processible. So what does it mean is that if we today in most of our products use activated carbon and we want to use our curved graphene, then any production manager will come to our research and development guys and tell them, I will not change my machines, I will not change my processes, and for good reason, because the company management will say, we have just made all these investments in these machines. Let's not change them. Why should we if we can further use them? So that's another thing of bringing a material invention to an actual product innovation. Is ideally you can use your material with no process change, and that's the case with our curved graphene. And why we like it so much is that we can still use aqueous mixing, we can use still the slot die coating, we can still use roll-to-roll electrode processing, and we can still use the same calendering machines that we are using today. So there's no additional money to be spent on new machines, and there's no new processes to be learned. That's a big impact. Don't think that if you have a new process that works well in the lab, that you take half a year and carry it over to application. It rather takes 5 years to carry it over, if this is not a process that is already used in the industry. So think about always when you bring in a new material innovation, think about how can this material be processed. Is that a process that you can actually use industrially? Maybe it is a process that is already used industrially, then it's great because you have the machines available. But if it's something completely new, then it's a great invention, but it doesn't necessarily make a great innovation in a short period of time. Yeah, here I already talked about a little bit about the cost. Yeah, so moving from these standard carbons that you have today in the market to other carbons that never made it in the end to the market has a cost impact. And I really encourage you to, whatever material you are researching, have a look into the cost structure of the final product, because you often see arguments, especially in energy storage, which relate to, okay, we use sodium because sodium, for example, is much cheaper than lithium, which is true, and is much more abundantly available than lithium. It's also true. But if you look at the cost of the cost percentage of the lithium content in the lithium-ion battery, then you will see that lithium makes up only a couple of percent of the overall lithium-ion battery cost. A lot of the cost today is the other materials, as well as how you process. So it's something where I would always say, if you want to make the cost argument on the whole product level and check what are the other components. So in this case here, the cost argument carries quite a lot of weight for any of the components because they share an equal amount. So today in a supercapacitor, you have an equal share of electrolyte, electrode separator, and cell parts in production. The cell parts in production, with further scale, it goes down. So the materials take over more, which is natural. In lithium-ion batteries, you're already there. But still, for example, if you have a 10% cost increase on a separator, it only means a very small increase on this overall cost percentage here, because the electrode and electrolyte make up most of the cost. So that's the logic that you can follow as well when you search for cheaper materials, for example. Another thing is purity. So one thing that we do in supercapacitors, of course, is lifetime testing. And we had this one material by industrial carbon manufacturer that they sent to us, and it was at very high gravimetric capacitance, 135 Farads per gram, or 35% higher than what you get with normal activated carbon. And this was also carried over into volumetric capacitance, so very nice volumetric capacitance. But as soon as you did the lifetime test, you could see that this carbon survives instead of 1,500 hours at 65 degrees C and 2.85 volt. It only survived around 200 hours. And that, of course, is a big problem because even if you have 30% more energy, if you need to oversize your whole application 5 times for lifetime, then 35% is dwarfed by this and doesn't bring you any impact. Same for cost impacts, by the way. So you could, of course, use a cheaper carbon with less purity, but again, you would, in the end result, not have a cheaper product. You would actually have a more expensive product if the lifetime doesn't fit. So I will now conclude the talk, and sorry for jumping in between different topics. These were rather examples where you can look out for, but supercapacitors are, of course, quite optimal for high power applications, but that doesn't mean that they are optimal for all applications. So it means that, again, keep the application in mind. What are you developing for, and be realistic about it. So what we normally clearly say is that we don't try to compete with lithium-ion batteries, because it would be nonsensical to do so in terms of energy density. But what we do is we look in the application where lithium-ion batteries have a very hard time supplying power, have a very hard time having enough lifetime, and that's where the supercapacitor technology makes sense. Currently, supercapacitors definitely lack energy density, and they can be improved. That is true. But if you move there with activated carbon, so far the only things that we have seen is that you always improve one property and you kind of lower the other ones. So you maybe improve gravimetric capacitance, but the volumetric capacitance is not increased, and it actually is lower. Or you increase both gravimetric and volumetric capacitance, but you have bad lifetime, or you have high cost, or you need to change your process, or the carbon becomes not processible by standard coating processes anymore. So these are the kind of things that me as an industry person now normally looks at. When I read an academic publication, then I do not read any of the, I read them of course, but I do not care that much for any of the numbers that you want me to see. Like, I found this material very high capacitance. I rather look at the numbers that you don't want me to see. So how do you process it? What could be the cost of such a material? Is there anything kind of hidden? Like, does this material suddenly give me very high resistance in the electrode? Yeah? So these are the things where I am always very grateful if somebody is very transparent with their data and says, yes, we have improved this greatly here on this side, but all the other sides here, or this one thing, is a big problem, and we will work on this. And it can be very helpful for you as well in academia, because it will help you to actually work out what should you be working on next. So if you increase the capacitance, for example, but your resistance is still very bad, then you know, okay, now I can work on that part, because that is the part that is stopping me from turning this invention to an innovation. And with that, I would like to actually end my talk and give you a little bit of time for questions. So I think I'm a little bit over time, but thanks again. And yeah, question away.
Thank you, Sebastian. I guess we do have time for questions from the audience. Maybe just raise your hand and I can unmute the person and ask questions. Okay. Yes, Jainul, unmute yourself and you can ask a question now.
Hi, Sebastian. First of all, I would like to thank you for your nice talk. You have mentioned one very important point, that more active sites in the material negatively influence the cycle life. As you mentioned, you have more capacity, more the specific capacitance is the less cycle life. So could you be able to elaborate that a bit? Tell us a bit more about that.
Sure. So the one thing is that you can, of course, treat it from a very just from the material standpoint and look at, okay, how many active sites can I have? What will this do to the lifetime? The important thing is that every supercapacitor manufacturer will evaluate the material not by its oxygen content or nitrogen content or whatever, but by its performance in the device, and normally in an industrial device. So whatever data you have on the small lab cells and so on, it's always good to give an indication, but the real proof always happens in the large devices. So these are these very big cells here, which are made. The surface groups that you have on activated carbon play an important role also in the processability. So you actually don't want 0 surface groups, because that normally means that you cannot mix your carbon with water anymore, or you cannot mix it well with other solvents. And that is where you kind of need to strike a balance of having the surface groups that you need, but having as little as possible, because normally these act as active sites where the electrolyte degrades. And then, of course, it's always the question, what kind of surface groups? For us as a manufacturer, we normally don't look into, is it a nitrogen surface group or what not, because we don't care about these details. We care about the lifetime measurement result. And as long as that looks good, then that's fine for us.
Sebastian, I have a quick question here. Now, you showed the device. It's quite big. Now, in academia, we always have this issue of scaling up, because not all the labs are capable of scaling things up. So what would be an acceptable size, and what would make sense where, we can bridge this gap between a coin cell testing and large scale testing? So it's an important thing for us to think about.
Yeah, there are 2 main aspects. What kind of lab device you should use if you want to investigate industrial cell size properties. So it can be actually quite a small device, because there are industrial supercapacitors that are quite small as well. So it's not about the size itself, it's about 2 main points. One is try to have a cell design where you have actually welded connections between the cell body, the body where you actually put the electrodes on to measure your device, and the actual electrode. So whether that's be a spot welded or ultrasonic welded connection, something welded, because that way you will be actually able to measure the resistance of your coating and your electrode, and not the resistance that you have between the 2 metal surfaces that barely touch. That's point number 1. The second point, and that's something that's very hard to do, but now several research groups are working on this, and I'm very sure you can come up with cell designs for this that are small, is gas evolution. So why the industrial cell size needs to be evaluated today by us is that you can have very good lifetime results, for example, in small cell sizes, but you go to the large cell size, and after around 10% of the lifetime, the cell bursts. Yeah, so the overpressure valve opens, and that is because gas evolution is very hard to measure in small sizes. So here there is some work being done also by Andrea Barducci, for example, on integrating gas like pressure sensors in your cells. But that also requires you to work on fixed electrolyte amounts. Maybe one thing that I can give you here is also the hint of looking how the industry actually produces cells, is that you normally have a standard cell with a standard process how to make it. So if you run your lab and you want to have like a good, you want to have a good standard cell, and it should be like this, that if one guy builds it or the other gal builds it or whoever builds it, it should be the same cell. That's the important part. It's very hard to do, but it is a very great reward if you do it right.
Fantastic. Maisam, it's time for you to ask a question. You raised your hand.
Hi, Sebastian. Thank you so much for the great talk. Sorry if here is a bit noisy. I'll try to move the microphone a bit closer. Can you please give us a few indications of metrics of a carbon that can be considered, as you said, a innovation, right? So something that can be translated into a product, such as like ESR in electrode level, such as volumetric, gravimetric capacitance, cost, these sort of things?
Yeah, so I think the very first thing that you should do when considering these, set up a standard in your lab. Use an industrial carbon that everybody's using. So there are coconut carbons that everybody's using today as a standard to validate your methods. Yeah, so to find out what gravimetric, volumetric capacitance, what kind of ESR do you get with applying your methods to this material, so that you have a comparison point. Because comparing your results to the results obtained by somebody in the industry making their electrode on a large industrial coater and everything, this will not bring you anywhere. You're comparing apples and oranges. So set up the standard. I think that's the first important part. Then if you talk about which properties you should improve and by how much, of course, any improvement in volumetric capacitance in your electrode is a great thing because it increases the energy density. Increasing volumetric capacitance normally also means that you decrease resistance, because volumetric capacitance is measured by electrode density. So if you have a very dense electrode, you normally have very good connection between the particles and the aluminum foil or whatever foil you're using, and that normally means that you have low ESR. So lower ESR also very important. If you are able to increase capacitance, but the ESR also goes higher, then make the calculation of, you can always calculate on device level. Yes, you can always calculate, if I now have a power pulse that runs over this device, and I lose more energy in the ohmic drop because of that higher resistance, is that compensated by the higher energy that I actually have through the higher capacitance? So that you need to calculate in the individual case. And I think the most important part to look at is if you increase, so it's basically the supercapacitors, it's very simple. It's just these two properties, capacitance and ESR. The other thing to look at, and that's the thing that in the end makes the decision if somebody wants to use that carbon, is cost. So do you have a good idea of how expensive this carbon will be? And it needs to be at the cost levels of today's activated carbons, which is, there's a rule of thumb for anything in supercapacitors to be to cost less than around $20 per kilogram. Yeah, then you come into a good range. I would even say that today you are already at rather $15 per kilogram, where you need to hit that. That's US dollars. Yeah, and then the second thing is processibility. So if you can make your carbon. If you can make a carbon, but you can only coat it with some elaborate coating technique that nobody's using, then it's highly improbable, even with very big advantages that you get on the material level, it's highly improbable that somebody will use it in their factory, because they would have to buy new machines and set up everything anew. That's a huge risk for them.
Thank you, Sebastian. Do you have any questions from the audience? Oh, my son once again. Yes, please.
Yeah, since no one is asking questions, I will take the luxury of asking two questions. I could see from your slides that the main or the gem of your product is basically the curved graphene, and basically it's the innovative nanomaterial which you are using in improving the performance of your products, basically. So can you give us a little bit of idea about, what do you mean by curved graphene? I've heard graphene a lot, worked with graphene, but curved graphene is a bit new to me. If you can give us a bit of details about that, would be great.
Sure. So curved graphene, first of all, is an oxymoron. So any physicist will tell you that curved graphene doesn't exist, because graphene is flat by definition. So of course, curved graphene is smart name that we came up with for our material. But what it essentially is you can imagine to have your flat graphene layer, yeah? And if you want to utilize that surface area, in theory, you have this very nice large surface area. But in practice, if you throw graphene nanoplatelets into solution, they cling to each other and they block the surface area. So what we did is we took this flat layer of graphene and crumpled it up, yeah, like a piece of paper. So in that, imagine that just take a piece of paper and crumple it up. In that piece of paper, you still have the same surface area that you would have before on the flat sheet of paper, but you have it presented in a way that it cannot stack anymore with other pieces of paper, and it cannot block the surface anymore. So that's what essentially curved graphene is. And on a chemical level, why do we call it graphene, or what's the graphene nature? Is that curved graphene has around 20 times the conductivity of activated carbons. So it plays rather in the conductivity, or even surpasses the conductivity of conductive additives. Of course, that's not the conductivity that you would get from graphene. But then again, this curved graphene, this crumpled up graphene layer, has a lot of damages to it, where this sp2 carbons are kind of broken up, and then you lose the conductivity in these spots. But generally, if you check the configuration of the carbon atoms in our curved graphene material, then you will find a lot of sp2 hybridized carbon atoms, which are the part normally of the graphene layers. So that's why we know it has graphene nature, but it does away with most of the issues that you have with applying graphene into an actual electrode, especially if you want to use it in bulk. And the nice thing about our graphene is really, about our curved graphene, is that we can use it in bulk the same way that you would use an activated carbon. We have a black powder, we throw it into a mixer, we coat it with the same methods that we use for activated carbon coating, and we can use exactly the same machines. So again, there you have it, your processability. Yeah, that's why we like it so much. It's not only a better material, it gives also the same processability as we have with other materials.
Thank you.
I'll probably thank Sebastian for his wonderful talk, giving us insights into what's happening in transition in research to innovation. It's so heartening to see that the innovations in supercapacitors are reaching real life applications, as you discussed. And one of the things which you talked was that there are many applications in which supercapacitors has a potential market, and maybe it is dependent on how companies explore that space. There's a room for everyone. A lot of companies are doing this innovation, but the market space is probably quite large. So with that, I will probably thank Sebastian. It was a real pleasure to have you here, and we'll conclude here. Somebody has joined. Ashok has joined just right now. But thanks, Sebastian.
Yeah, thank you as well.
This talk will be is recorded, so it will be available for everyone to view. Thanks.
Yeah, thank you. Okay, bye-bye.